Next we have exercise 22. In this one, we define a new function like the functions tau and sigma, and that function is sigma suffix s. S is some non-negative integer, and the value of this function at a positive integer n is given by this sum. It is the sum of the s powers of all the positive divisors d of n. And then we have to verify some facts about this function. So there are two other parts. This is the first part. So here we have to prove that if the value of s is 0, then this sigma 0 is nothing but our function tau. And if s is equal to 1, then sigma 1 is our sigma. So this sigma s generalizes both these functions. So let's first see how this is true, and then we will go to the other parts. The solution is almost trivial. We straight away calculate the sigma 0 value of some positive integer in any positive integer n, and by definition it is just this. In place of s now we have 0, and of course all the positive divisors of n are involved in this sum. So you see that each term of this sum becomes 1, and you already know that this is what tau of n is, because we are adding as many 1s as there are positive divisors of n. So we get the number of positive divisors of n, and because this is happening for any n, so as functions sigma 0 and tau are identical. Similarly, the other this claim will also come. Let's see that. So this time we take sigma 1 and calculate its value at n. Again, by the definition, this is just this sum where in place of s now we have 1. So you get this, and this is just the sum of all the positive divisors of n, which is what sigma of n is. And that is why sigma 1 and sigma are identical. So that's part A. Next, let's see part B. Part B states that the function sigma s is a multiplicative function. Look at this function, f of n equals n to the power s. This is a multiplicative function, and it's almost trivial to verify that it is a multiplicative function. Because of this fact and theorem 6.4, we have what we want, that sigma s is itself multiplicative. You go back to the statement of theorem 6.4 and see why this conclusion can be made from these two things. Next we see part C. In part C, the prime factorization of a positive integer is given, where the primes involved are these p1, p2 up to pr, and the exponents are k1, k2 up to kr, respective exponents. If so, then the sigma s value of n is this product, where you have one factor for each prime. For example, the factor corresponding to the prime p1 is p1 to the power s times k1 plus 1 minus 1 divided by p1 to the power s minus 1. Similarly, the one corresponding to the last prime pr is this, pr to the power s, so that s is always there, but then along with pr we have the exponent of pr, actually 1 plus the exponent, kr plus 1 minus 1 below divided by pr to the power s minus 1. So let's solve this one. In the beginning of the solution itself, we simplify things by noting that sigma s is multiplicative, which we proved just now. And because of that, it's enough to consider only this case, where our n is a power of some prime. And by now you know very well why this is enough. So we just straight away calculate the sigma s value of n when n looks like this, when n is this. So this will be the sum of all s powers of the positive divisors of p to the power k, and those positive divisors are this 1 p square up to p to the power k. And you can clearly write this sum using the rules of exponents, usual rules of exponents like this. 1 plus p to the power s, then the square of that, So you can interchange 2 and s. That's what we are doing here. Here also you can interchange k and s, and you do the same thing to the intermediate terms as well. And then it is a finite geometric series whose common ratio is p to the power s, so you know what its sum is. The common ratio to the power k plus 1, because it ends with k, minus 1 divided by common ratio minus 1. So again, once more you apply that rule of exponents. So you get p to the power s times k plus 1 minus 1 divided by p to the power s minus 1. And that's it. This is what the claim is when n looks like this, because there is only one prime p. Using this and the multiplicative nature of f, you now have the general claim proved for you. And with this set of exercises ends. There is another one, but number 23, we are not doing odd exercises here. Those things are left to you. So next week we can start the next section on Möbius inversion formula. So see you next week with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.